Hello, Honors Chemistry students. This is Mr. Spurk, and this is your Chapter 7, Section 1 notes covering ions. So first thing, a little bit of a review. Valence electrons are those electrons in the highest occupied energy level, and they largely impact the chemical properties of each element. The representative elements, remember our groups 1A through 8A, we can just look at the group number and determine that that is how many valence electrons that element within that group has. And remember that helium is the only exception. Helium, although it is in group 8A, only has 2 valence electrons. So valence electrons are usually the only electrons involved in bonding. And because of that, we will focus on drawing electron dot structures. And these are diagrams that show valence electrons. So you can see here, these are the group A elements for the first 4 periods, and these are the electron dot structures. So you see that in group 1A, we have 1 valence electron. So you see the element symbols with their 1 valence electron drawn in right here. So then you go to group 2, they have 2, 1, 2, group 3, they have 3, and so on and so forth. So these are Lewis dot diagrams or dot structures. So again, these only show the valence electrons, and there are very simple steps to draw these. The first part is you draw the element symbol, so that's denoted here by that giant X. Then you determine the number of valence electrons that element has, and then you place 1 dot per electron around the element. Now, you'll see here that there's a counting symbol or a counting sequence that starts here. It says 1 on top, then 2, 3, 4. Then we go around again, 5, 6, 7, 8. It does not matter where you start. In this diagram, they start on the top, then they go around to the right. It really doesn't matter. Typically, I start on the right-hand side. The only thing that does matter is that you start somewhere and that you go around all 4 sides first, then go around again. So how they're spaced out like this, 1, 2, 3, 4 to get all 4 sides, then go around again, 5, 6, 7, 8. So for example, let's look at bromine and then magnesium. So bromine is a halogen in group 7, therefore it has 7 valence electrons. So we start by drawing the symbol for bromine, Br, and then we just draw our electrons. 1, 2, 3, 4. Go around again, 5, 6, 7. And there you have it. Let's look at magnesium, Mg. Mg is in group 2, so it has 2 valence electrons. So 1, 2. And that's a Lewis dot diagram. So the octet rule. Noble gases, we know from last chapter, are inert in chemical reactions. They are stable, and remember that they are stable because they have a full outer shell. They have full s and p orbitals. And Gilbert Lewis in 1916, he explained why atoms form certain kinds of ions and molecules. And he called this the octet rule. And we've briefly mentioned the octet rule. The octet rule says that in forming compounds, which remember means 2 or more elements together, atoms tend to achieve the electron configuration of a noble gas. And remember, we said this is because they want to fill or have a filled energy level. Metals, we've discussed, tend to lose their valence electrons, leaving a complete octet in the next lowest energy level. And nonmetals tend to gain electrons or share them with another nonmetal to achieve a complete octet. So cations, remember cations are positive. Atoms lose electrons to attain the noble gas configuration. For example, sodium. Sodium is in group 1. It has 1 valence electron, but the sodium ion is going to lose that 1 valence electron, and if it loses 1 valence electron, it becomes Na+, Na positive. Next up, we have calcium. Calcium is in group 2. In order for it to have a full outer shell, it's going to lose those 2 electrons. So if it loses 2 electrons, Ca2+. Now, the transition metals also form cations, but they do not always achieve the noble gas configurations. Remember, we have not discussed how we know exactly how many valence electrons each of these metals has, and we said that they can form various ions. So their charges can vary, and they're denoted by a Roman numeral. So you see here that the Roman numeral for the number 1 denotes 1 plus, 2, 2 plus, 3, 3 plus, 4, 4 plus. This is pretty much the only Roman numerals we will see and need to know. Beyond that, V is 5, VI is 6, and we may see VII, which is 7. So let's look at copper 1. So again, remember that copper 1 implies that it is 1 plus. So all we need to do here is the symbol for copper, plus. Tin, IV, means 4. So here we have the symbol for tin, 4 plus. Iron 3 is Fe, 3 plus. And copper 2 is copper 2 plus. Now, if someone just says it's a copper ion, we don't know what charge this ion has. So when we're writing the names of transition metal ions, we must include a Roman numeral after it. Otherwise, we don't know what charge it is. Anions, remember A negative ion. These atoms gain electrons to obtain the noble gas configuration, and these are typically the nonmetals. So fluorine is in group 7, so it only needs 1 more to complete that octet. So since it gains 1 more, it becomes 1 minus. Oxygen is in group 6, so it has 6 valence electrons. So it only needs 2 more. When it gains those 2 more, it becomes O2 minus. So in review, atoms are most stable when they have noble gas configurations or a full shell. And how many electrons does the atom need to gain or lose to be like a noble gas? This is the question you want to ask yourself when you're trying to figure out how many electrons it's going to gain or lose. And then the charge, or the oxidation number, that's the number that represents the number of electrons lost or gained. So for example, Ca2+, this is considered the charge or the oxidation number. As always, all the information on these slides has been acquired and adapted from Pearson Chemistry, 2012 edition of the textbook, resources CD, and pearsonchem.com. Have a great day.